In this video, we're going to be discussing another type of rigid transformation. In this case, we're going to be discussing reflections, okay? And a reflection, pretty simply, I'm going to kind of try and illustrate over here. We talk about two different types of reflection, but say we're given a graph, maybe the root function was the last one we discussed in the other video here, and we say the root function, and I necessarily wanted to reflect this about the y-axis, okay? We're going to talk about how I might alter the equation of this, which would be f of x equals radical x. Okay, but how could I mess with this function so that it actually reflects about, say, for example, the y-axis? Okay, and that'd be a helpful thing to point out. We may even we will discuss, how we could necessarily change the function to reflect it about the x-axis. Okay, but that's the whole intent of this video this time. Okay, so we're going to be discussing reflections. And so first of all, as I'm erasing this, or undoing rather, would you look over here on the left, and I've written already two statements, but we say x-axis reflection and y-axis reflection, okay? So in both instances, you'll see here that I'm defining some function h of x, okay? So the reason why I use h of x is because I'm reserving f of x to represent a parent function, or a very, very basic form of a function. Nothing's been altered about it. It is the most, it is the purest sense of a function. So like, for example, we're going to be dealing with that root function, but we say f of x would be square root of x. This is called the root function, okay? So when I say like h of x as being an altered form of f of x, I may start with something like, might as well, we say h of x is equal to the negative square root of x, okay? So the first thing we'll do is let's kind of interpret how this is different than the original function, okay? So you notice here h of x equals negative square root of x. My number one thing that I ask people to do first of all is please identify the parent function we're dealing with here. And of course the parent function is going to be the square root function. So here's what I know. I know f of x and square root of x, they mean the same thing. So going back down over here, what I'm going to do is I'm going to point this out. We have the square root of x is right here. That's the same thing as what we call the parent function f of x, except for it's got a negative in front of it. Okay, so now what I can do is I can rewrite this, or we can rewrite this, we say h of x, okay, is really the same thing as negative of the parent function f of x, okay? But you'll notice here that the negative is actually in front of this, okay? Another way to look at this is like we're making, negative f of x, right? Negative f of x. We're kind of saying a negative y value, but I'll leave that aside for later. We say, but negative f of x, let's go ahead and go back up here and refer to what we started with. So we say if h of x is equal to the negative of the original function, then what we necessarily know is that this is going to exhibit x-axis reflection. Let's go ahead and draw this situation. We'll sketch it rather, because my drawing skills are just, they're rubbish. But anyways, okay. So we'll get our parent function rocking here. Our parent function was the root function, just f of x equals square root of x. It started at 0, 0, went up 1 over 1, proceeded to the right. Okay, looks like this. We say here's f of x. So now, by negating this f of x value, or saying I have a negative in front of the f of x function here, we're going to exhibit x-axis reflection, okay? So if you can imagine this being reflected about the x-axis, that's kind of like we would say, okay, so this point here, right, this point here, which was 1, 1, it's actually going to reflect over this axis right here. So it's now going to be down here at 1, negative 1, okay? And so we say its reflection would look like this. And we'll give this dotted function, this dotted graph, the name h of x. Okay, so let's explore, so what is y-axis symmetry going to look like? And so I probably better switch our colors out here. Maybe we go to this color right there arbitrarily, and we say, okay, so instead of h of x, we'll call this one g of x, just for the sake of being distinct from h of x, hopefully, or it doesn't have to be, but it will be in this instance. I'm going to say, so g of x. In this case, g of x is not going to be negative the square root of x. I'm actually going to call this the square root of negative x. Now, the first thing I want to do right here is actually point out the fact that there's a negative inside this radical. However, it is attached to the variable x. So maybe it'd be helpful if we start off by making a table here and say x and y. But let's fathom we actually did try to plug in some negative x values, like negative 4, negative 1. We'll even plug in 0. But if you put in a negative 4 in here, that'd be like saying, okay, so g of negative 4 would be now square root of negative blank, and we're plugging in negative 4. That double negative actually flips this back positive, and we say, okay, so this would be 2. So the neat thing about this is, with a negative on the inside, we can actually explore x values to the left with a root function. But we'd say we'd have 2 here. Likewise, if we plugged in negative 1, negative 1, the root of that would be the root of 1. We have 1. We have 0 here. So plotting these points, we say, okay, so 0, 0, negative 1, comma 1, and we say, okay, so negative 4, comma 2. I'm kind of sketching this in here, you'll see this. But really what I wanted you to notice was this. This is no more than the original f of x function, but reflected about the y-axis. So let's go ahead and I'm going to pull this over here. I'm going to say we started with g of x equal to square root of negative x. Okay. So the bottom line is the negative was inside here, but this looks a lot like our parent function, the root function. Okay. We want to know how is it different though. And it's different because it has a negative inside there. So the way we would obtain this, we say this is the same thing as f of negative x would mean, then wherever we see an x up here, okay, we'll plug in a negative x, okay? And so this is actually equal to our g of x. That's what that is right there, is our g of x down here, okay? So it's the same as f of negative x, but by f of negative x, what we're really recognizing is that we're reflecting about the y-axis. So let's choose another parent function arbitrarily. It's good to go through several examples, especially with stuff that tends to be confusing for people, and especially probably the way I explain it. If you're still upset after watching this video, you can write me hate mail. But anyways, how about we call a function, we'll call it s of x. S of x, and we'll define this as being, say, oh, I don't know, x squared, okay? So what I'd like to do this time is say, okay, so f, you know what, no, not x squared, no, that's silly. What I want to do is s of x is negative x squared, okay? And you know what, the interesting thing about this is I'm putting this up here on purpose because you're going to notice, first of all, our parent function in this instance, a parent function would be f of x equals x squared, which happens to be a parabola. So we say this parabola would start at 0, 0. Go up 1 over 1. I'm just sketching in the parent function here. Left 1, up 1, left 1. We say, so here's our parent function. Okay. So now observing this new function, you'll notice that this negative is not on the outside of this x squared, but it's hanging out inside with the x squared. In other words, this s of x is the same thing as kind of like saying f of negative x. It'd be like f of x if we had plugged in a negative right there. This would have been negative x squared. Okay. So the weird thing about this is negative x squared, of course, is just x squared, which is going to look exactly like this original parent function in the first place. But what I'm trying to point out here is this. F of negative x, okay, plugging in a negative x here into the original parent function causes y-axis symmetry. And so this y-axis symmetry, if you can imagine, or symmetry, excuse me, reflection, if we were to necessarily like reflect this about the y-axis, it would reflect onto itself, okay? So just to show you, you know, maybe we do an x-axis symmetry, and we'll switch over to pink here. X-axis symmetry, that'd be like if we had t of x, and t of x was negative. Now the negative's out front, not inside here with this x squared. But this would cause x-axis symmetry, or reflection, so this would flip basically everything over on our original parent function and cause it to open down. But of course, if you take an algebra with your extensive knowledge of polynomials, you would know that just a negative leading coefficient would cause this to open down. So it makes sense that it would just be the original blue parent function there flipped about the x-axis.